Okay, September 9th, 2012, we're going to get ready to record 16A. Sorry I got it up a little late. Hopefully people get a chance to see this yet tonight. If not, we'll be going over it tomorrow. But if you get a chance to watch it first, that's great. Got a chance to see the Indians win big this weekend, and followed up by the Bears winning a big game tonight, so it couldn't be any better. Hopefully the Pack will take one on the chin, and all will be good. See everybody in class tomorrow, and we'll talk about that a little bit more. But here we go. Chapter 1, Section 6A. There's only one lesson on Chapter 1, Section 6. It's on trigonometric functions. So, if you can imagine, last year you had 2 or 3 chapters in pre-calculus dealing with trigonometry, and it's all going to be in this one section. But we will continue to work on reviewing all of the trig material throughout the year, the identities that you need to know, the graphs that you need to be able to produce, and the equations that you need to be able to solve. But to start out with, we definitely need to be able to understand how some of these graphs look. So the first definitions that we have are a definition of a sinusoid. And you do need to realize that these things are called sinusoids when we're looking at the picture of sines and cosine functions. A sinusoid is a function that can be written in the form f of x equals a times sine of bx plus c plus d, where a, b, c, and d are real numbers. The inverse sine function is denoted by y equals sine raised to the negative first power of x, or the arc sine of x. And it is a function. And since it's a function, it has a limited domain from -1 to 1. Not that functions have to have limited domains. But in order to take the inverse sine, we must limit it to a particular domain and a particular range, because the sine function itself is not a 1-to-1 function. And we talked about what 1-to-1 functions were the other day. So we need to restrict the sine graph to a 1-to-1 portion in order to take the inverse sine of it. And that's why the domain must be from -1 to 1. But more importantly, why? When it asks for you to find the inverse sine of an angle, and it uses the notations denoted here, these two, if it uses that notation, you must only produce one answer between -pi/2 and +pi/2. This is something that should have been taken care of in Algebra 2 and pre-calculus. We'll continue to work on it, but you have to realize when it's written in this format, you give one angle for an answer. Same here with the inverse cosine. The domain's a little bit different, and the range is a little bit different. The domain's the same, actually, from -1 to 1. So that means we can only take the inverse sine and the inverse cosines of numbers between -1 and 1. If the problem asks you to find the inverse cosine of 2, you simply say, cannot be done. There is no solution. But for an inverse cosine, the angle must fall either in the first or the second quadrant, because the range of acceptable answers is from 0 to pi, or on one of the axes. Okay? Where the sine, the inverse sine, is either the first or the fourth quadrant, because the answer must be from -pi/2 to +pi/2. The inverse tangent function is denoted by y equals the inverse tan, or tan to the negative first power of x, or y equals arctan. And this one, we can take the arctan of any number, because it's the opposite over the adjacent. And the opposite could be a lot larger than the adjacent or a lot smaller. We can take the domain of any number, or we can take the inverse tan of any number. The range of acceptable answers, though, is from -pi/2 to +pi/2, non-inclusive. So again, the angle is going to fall in either the first or the fourth quadrants when we do arc tangent. So I always remember it this way: arc sine, arc tangent. You must give an answer either in the first or the fourth quadrant. Arc cosine, you must give an answer in the first or the second quadrant. And we will talk more about it tomorrow in class, so that hopefully you can see why that is when I draw the, I actually draw the Cartesian plane for you and show you why it falls in those particular quadrants. For today, the first example here is really something, I don't even know if the book has these problems anymore. It used to be in the old version of this book, and I've kept it in the notes. I think it's good for you to know. Sometimes students forget how to find the distance of an arc length, okay, a portion of a circle. And there's a nice little formula, if we can remember it, that says S equals R times theta. S stands for the arc length. Not exactly sure why they use S, but every book does. R is the radius of the circle. The radius that forms a complete circle, of which we're looking for part of it. We're looking for an arc of that circle. And theta is called the central angle, but the most important part about theta is that it must be in radians. One more reason why we are always in radian mode in calculus class. This whole degree nonsense is kind of silly. It's too bad that it's taught at such a young age, because the real world measurement for angles is radians. And the sooner you can get to using radians, the better you'll be for everything mathematically from here on out. So this first problem here is really as easy as it gets. If we want to find the arc length, given the central angle and the radius, the arc length is simply going to be the radius, which is 2, times the angle, which is already in radian form, because it has pi. And there's no degree symbol after it. So if we cancel, it is going to be 5 pi over 4. That's the arc length. Now, it is an actual length that we want to know. So if you'd like, you can certainly use your calculator, figure out what 5 pi over 4 is, but you can leave your answer in terms of pi. For me, is fine. But if we want to figure out what 5 pi over 4 is, we go to this. 5 pi divided by 4 divided by 4, and we get an answer of 3.927. So S is approximately 3.927. Okay. On the second example here, in this particular one, they give you the angle. They want you to find the radius if the arc length is 3 pi. Just plug in what you know. The arc length is 3 pi. The radius is what we're looking for. The angle is pi over 6. So now if we just multiply by the reciprocal, multiply by 6 over pi, 6 over pi, and reduce, the radius will be 18. Now they don't give a units of measurement here, but if they did, if they said that the arc length was 3 pi inches, then the radius would be 18 inches. Understand that the arc length and the radius are a linear measurement, so they will be measured in inches or centimeters or feet, a linear measurement. But the angle is in radians, and radians is already a real-world measurement, so it doesn't have anything after it. You could certainly put RAD after it if you want, but it is not. It's a real-world measurement. We do not have to put anything after it. The number itself is good. Here we go. Example number 2. Give the measure of the angles in radians and degrees. Give exact values whenever possible. Here's the deal on these particular problems. First of all, if it uses this notation here, sine to the negative first power, tangent to the negative first power, we give only one answer. You have to know when you give only one answer and when you give multiple answers if they give you an expanded domain or range of acceptable answers. You have to read the problem carefully. On these, we only give one answer. And what I expect, essentially, is that if it is a 30, 45, 60, or 90 degree angle, or any of those multiples, I expect you to give the answer as an exact answer, not something that you're getting out of your calculator. Now, unless I take your calculator away, I can't prevent it on a problem like example number 1A here, except for the fact that I will require you to draw the correct triangle in the correct quadrant. If you don't do that, you will miss points. There are problems like this on the test. It's my way to ensure that you are just not simply typing it in the calculator, but that if you did not have your calculator, you would be able to tell me what the arc sine of 1/2 is without a calculator. We need to be looking for arc sines of things like 1/2, square root of 3 over 2, 1 over the square root of 2, which is the same thing as square root of 2 over 2, since it's rationalized. So those types of numbers, we should be able to find the arc sine and the arc cosine of without a calculator. Likewise, for arctan, the arctan of 1, we need to know is a 45-degree angle. 1 over the square root of 3. Square root of 3 over 1. We need to know how to find those without a calculator. Draw a picture in the correct quadrant and you should be able to find it. As a matter of fact, on every one of these problems, I'd like to see you draw the triangle in the correct quadrant so you have an idea of where your answer should be even when you use the calculator to see if it makes sense. So, example number 2, A. This is the same thing as saying the arc sine of 1/2. In order to find the arc sine of 1/2, first of all, you need to know on an arc sine, I have to either use the first quadrant if it's positive or the fourth quadrant. Since this is positive, it's the arc trig function of a positive number, it will always be the first quadrant. That shouldn't be the difficult part. If it's the arc sine, arc cosine, arc tan, for that matter, arc cosecant, arc secant, arc cotangent of a positive number, it will always be in the first quadrant or on an axis if it's 1 or 0, okay? But it'll be in the first quadrant. That shouldn't be the difficult part. When you take the arc sine or arc cosecant of a negative number, you must use the fourth quadrant. When you do the arc tan or arc cotan of a negative number, you must use the fourth quadrant, and only the fourth quadrant. If you do an arc cosine or arc secant of a positive or of a negative number, you must use the second quadrant because it's still positive in the fourth quadrant. And we have to have a continuum of output answers, meaning that it has to go from 0 over to pi. It's one continuum of acceptable range of answers, okay? So that's kind of a summary on a lot of different things, but on this particular problem, we're taking the arc sine of positive 1/2. I'm going to draw myself a triangle every single time, and I will do it in class a lot to the point where you'll probably get tired of it. I understand, but the more you see it, the more you'll get it down. We should know SOHCAHTOA, which means sine is the opposite over the hypotenuse. The opposite in this case being 1, the hypotenuse being 2. And we should have the triangles memorized that I talked about last week in class. This is 1, 2, square root of 3. If you do not have your 30, 60, 90 triangle memorized, your 45, 45, 90 triangle memorized, and the unit circle memorized, you need to have that done before you come into class tomorrow. That should have been done a long time ago. Across from 1, we know is the 30-degree angle. Across from the square root of 3 is a 60-degree angle. The hypotenuse is obviously a 90-degree angle. By looking at this, we now know then across from 1 is the 30-degree angle, so this arc sine is a 30-degree angle. For now, give it both in degrees and radians, although on the AP test, they'll always ask for only radians. You need to know that 30 degrees is the same thing as pi over 6. You can certainly convert by multiplying by pi over 180, but if you have to do that every single time, you're going to waste a lot of time converting. You need to know that 30 degrees is pi over 6, that 45 degrees is pi over 4, that 60 degrees is pi over 3, and that 90 degrees is pi over 2, and then you should be able to find any rotation from that. And I will talk about that in class more, how you should be able to rotate in your head to be able to find angles quickly without having to convert it every single time. You should be able to do mental math to find a lot of these angles. Okay, the arctan of -5. Let's draw ourselves a picture. So every time I want to see a picture drawn, even on one like this, that we're going to end up having to use the calculator because I want you to think about what it is that we're finding here. We're finding the arctan of a negative number. Well, it's negative, so we cannot use the first quadrant. It's the arc trig of a negative number that you have to think. Do I want the fourth quadrant or the second quadrant? The only time we want the second quadrant is if it's the arc cosine or arc secant of a negative number. This is the arctan of a negative number. It goes in the fourth quadrant. Even a whole number like -5 can be written as a fraction. It's -5/1. So I know the opposite, because I'm thinking about TOA, SOHCAHTOA, opposite over adjacent. The opposite is 5. The adjacent is 1. I'm going to make the 5 negative because it's going down. So the nice part about it is the signs will take care of themselves if you draw it in the right quadrant. To find the hypotenuse, this is certainly not one of the triangles that we've memorized, but I can, 1 squared is 1, -25, or -5 squared is 25, add them together is 26. It's the square root of 26. That's the hypotenuse. But I'm not going to recognize that. I just draw it in there so that if they ask me, let's say that they ask later on for you to find the cosine of this. Now everything's done. The cosine would just be adjacent over hypotenuse, 1 over the square root of 26. Okay? You have to use your calculator on this particular situation. There's nothing we can do. So the inverse tan of -5. I'll go to the smart view. Inverse tan of -5. Second tan, -5. Understand that we're going to be in radian mode to start, so that's going to be radians. The nice part about it, if you want to convert to degrees, simply go to your mode, cursor down, go over to degrees, hit enter, second quit to get back to the home screen, and then just hit enter again. You don't have to retype it in again. And there are both the answers. -1.373 radians, -78.690 degrees. Okay? Let's write those down again. 3.927. Write that one down first. You don't have to put anything after it when it's radians. No symbol is fine. And then negative, well, I wrote down the wrong number though. -1.373. Sorry about that. Okay. Sorry about that. And then we'll go back to the angle in degrees, which is -78.690. All right. There's the first two examples. Some nice simple stuff. Then we're going to get into some graphs. We're going to graph a lot of these functions. We're going to look at a few of them right here. But it's hard to get a true good flavor of all the different types of functions that you're going to see in this particular section just online like this. I'll put up a few examples, try to work some out the best that you can. We'll work at more tomorrow in class. But the whole key to this is if you can draw the sine and the cosine functions, we really should be able to get anything off of those two main pictures. So for the first one here, y equals a sine of x, I'm actually going to talk through why it looks the way that it does. In other words, if I draw just the unit circle, 1, 0, 0, 1, -1, 0, 0, -1. In this particular situation, it only wants us to draw the picture from -pi to +pi. Typically, I like it drawn from 0 to 2pi, but that's fine. It doesn't matter. In the book, as a matter of fact, it says to draw 2 periods for any trig picture that they ask for, any trig graph that they ask for in the book. If you draw 1 period, I'm fine with that. All right? It has to be 1 period. The only thing that I request is that you must put where the y-axis goes, and it must be in its appropriate spot. You can't draw a period 2 cycles down the line. I want to know where the y-axis fits, and I'll explain that as well as we do multiple examples in class. To start with, when I'm drawing any trig function, the very first thing that I'm always going to do is start with a horizontal line, and this is going to be called my center line. And I'm going to label it accordingly. So in this particular case, they want me to go from -pi/2, so I'll start at -pi/2. And the key is, in a typical trig function, a sine or cosine, I can get a quarter period. It's really called a quarter period every pi/2 units. So if I take negative pi and I add pi over 2 to it, I'll get negative pi over 2. Add another pi over 2, I'll get 0. Add another pi over 2, I'll get pi over 2. Add one more pi over 2, and I'll get pi. And that's how it's going to be broken up right there. And if I just use my unit circle here, I can get a nice picture of this. Remember, when evaluating quadrantal angles, if I'm looking at the sine, I have to look at the y coordinate. So when graphing this particular picture, the sine at negative pi, this is negative pi right here. The sine is the y coordinate. The y coordinate at negative pi is 0. At negative pi over 2, this is negative pi over 2 right here. The sine at negative pi over 2 is negative 1. So I'm just going to estimate 1 unit away from here. Okay? At 0, here is the angle of 0. The sine at 0 is the y coordinate. 0 is 0. At pi over 2 is right here. It's the y coordinate. Pi over 2 is right here. Now I want this distance that going down from here to here to be about the same as the distance that I go up. So it looks somewhat symmetrical. When I'm back to pi, I'm back to right here, which is 0. And now I can sketch this curve. It is bowl-shaped up here. It is important that you shape this correctly. It's concave up, bowl-shaped up. And then it's concave down. That's how one period of the sine curve looks right there. Now, I could have kept going over here. I could have drawn another period that would look like this, because sine, cosine, tangent, and the reciprocal functions are called periodic functions. They go on forever and ever. They repeat themselves. There are a lot of different things in nature that actually move in this manner. So this is something that it's not just made up. We see it a lot out in the real world. Okay, that things that move as a sine wave or a cosine wave. So there are a lot of applications for these particular graphs. That's the first one there. In order to get the cosecant, here's the nice part about the cosecant and the secant functions. It's simply the same thing as the sine function, except for the fact that if I take the reciprocal of 0, at this point, if the sine is 0, if the sine of negative pi is 0 right here, if I want to take the cosecant of that, that's the reciprocal of 0. Well, you can't take the reciprocal of 0. It's undefined. So every time where the sine function would have crossed the center line, we need to dot in a vertical asymptote. And then what happens is, if I look at these numbers close to the x-axis around negative pi, they are small but negative numbers. And the reciprocal of a small negative number is a large negative number. So what ends up happening is, for the cosecant function, the low points go down and the high points go up, because the reciprocal of a really small number is a really large number. Okay? A number really close to 0. That's all we have to do with the cosecant. So the cosecant should be easy to graph. Just graph it like it's a sine. Put in an asymptote wherever it crosses the center line. Take the high points go up and the low points go down. And we can graph it quite easily. We're going to graph tons of sinusoids in this chapter. I'm going to just give you 2 examples, because I could sit here all night and try to produce example after example after example. I know you've learned a lot of different methods for trying to graph these. Mr. Hearn uses a rubber stamp method that he's talked about before, and if you want to use a rubber stamp to help you get that, that's great. I have no problem with that if that works for you. I really feel if you follow along with what I'm trying to do to break these down, I think you can graph these sinusoids without a lot of difficulty. It's gone really well the past few years. So hopefully, try to get this method down. I think it will work for you, as has been indicated by the last at least 3 or 4 years on the test. Very few problems with graphing the sinusoids on the Chapter 1 test the last few years. So hopefully you can get this method down. Because essentially what I'm going to do is I'm going to ask you to identify on every one of these problems the amplitude, the period, the horizontal shift, the vertical shift. I'm also going to ask you to find what's called the quarter period. I call it the increment, but it's essentially a quarter period. And then I'm going to ask you to draw the graph of the function. So on each one of these, the sooner that you can identify the amplitude, which on this problem, the amplitude happens to be 2. One thing to know about amplitude, it's always positive. Even if this coefficient in front of the trig function is negative, we always list the amplitude as a positive number because it's defined to be the distance away from the center line, the maximum distance away from the center line, either up or down for a sine or cosine function. And it will always be represented by this coefficient in front of the trig function itself. It's called the amplitude. It's the vertical stretch is another way to think of it. It's the way that we stretch a sine function vertically. Okay? The period in this particular case is the standard period. I'm sorry, it is not. The period in this case is going to be 2 pi over 3. Okay? A standard period is 2 pi for a sine or cosine function. For a tangent function, the standard period is pi. And we'll see a couple of those in the homework. But to find the period then, if there's a period change, it's always this coefficient. I told you wrong. That is incorrect. It's always the coefficient in front of the x that determines the period. What you do need to know is this, that the period of sine or cosine function can be found by taking 2 pi over the coefficient of x. It's the coefficient of the argument. It's not the coefficient of the function itself. So in this particular example, it will be 2 pi over 1/3. So when we flip, we will get 6 pi for the period. So that was my mistake on that. As I told you, I will make mistakes as we go. Generally, I'll get most of them cleaned up before we're done. But you may have to use your eraser even as you're doing some of these online lessons, so I apologize for that. The period is 6 pi. The vertical shift. The vertical shift I will end up calling the center line. And in this case, the center line is y equals 0. Or you could just say the x-axis. The center line is determined if there is a number that's added or subtracted to the trig function, but on an island by itself. If there is an additional constant term, ways to think of it, it has to be a separate term. It cannot be attached via parentheses to the argument. It has to be a separate term, and you'll see one in the next example. But in this case, if there is no number, if there were a +3 out here, then y equals 3 would be my center line. If there was a -5, then y equals -5 would be my center line. But we don't have that. Okay? And then the last one is what they asked for as a horizontal shift. I call a phase shift or a phase angle. I will say phase shift. And this is not terms that I've come up with. This is what a lot of other books use as well. It's called the phase shift. And again, the phase shift here is 0. We have a phase shift if we are adding or subtracting something to the x, to the argument. Okay? It will always be in parentheses. So here's how I remember it. Phase shift starts with the P. I only have a phase shift if I have parentheses. If there's no parentheses, you cannot have a phase shift. So it's one nice way to remember. Okay? So if I were to graph this particular picture right here, having this information, I would do the same thing that we did on the last problem, except I'm always going to find the quarter period, and I just call it the increment because I want to know that I'm adding it every time. When you think of an increment, it's something that you add to get from one to the next. The increment for sine or cosine, when I'm breaking these up, I'm always going to take the period divided by 4 every single time. In this case, the period is 6 pi divided by 4. When I reduce it, I get 3 pi over 2. That's the increment. Here's what the increment represents. When I go to graph this picture, all I need is this information right here. If I have all of this, it should be no difficulty Should have no difficulty graphing this. You're going to start the same way every single time. You're going to draw a horizontal line. Whether that is the x-axis or some other center line, but we don't know to start with, but that's fine. In this case, the center line is y equals 0. So this is going to be the x-axis. It's great if our center line is y equals 0. But if it's not, we're going to label the graph on the center line anyways. We're always going to start at our phase shift. In this case, we get to start at 0 again. So that's nice. And then we're going to add the increment each time. So in this case, it's 3 pi over 2. So I'm going to add 3 pi over 2. I'm going to add another 3 pi over 2, which is 6 pi over 2, or 3 pi. I'm going to add another 3 pi over 2. 6 pi over 2 plus 3 pi over 2 is 9 pi over 2. I'm going to add another 3 pi over 2. 3 pi over 2 plus 9 pi over 2 is 12 pi over 2, or 6 pi. Now, the hardest part about the method that I use is that you have to know this. You need to know how the trig function starts. Cosine functions start off the center line. Sine functions start on the center line. So in this particular case, I have a cosine. So at the phase shift, at 0, I'm either going to start above or below. If the coefficient of the cosine function, if it has a positive amplitude coefficient, you will always start above the center line. If this was a -2 instead of a +2 in front of the cosine, we would start below the center line. We would start down here, but that's not what we have in this particular problem. Okay? If this were a sine function, we would always start on the center line. If it has a positive amplitude coefficient, we would go up first. If it has a negative amplitude coefficient, we would go down first. So if you know how to start the graph and then transition into your first angle, you should be able to graph any of these. But you do have to memorize that little bit of information, how to start it. Once we have a starting point, we just know if I have a high point, I got to cross before I go low. I got to cross before I go high. And it's going to look like this. The very last thing that you're going to do when you are graphing any trig function for me, the very last thing that you're going to do is draw in the y-axis. In this case, we went through 0. You will not always go through 0, so you just estimate where it would be and then label accordingly. The center line is y equals 0, or the x-axis, however you want to label it. The maximum points are going to occur 2 units up from the center line because our amplitude is 2. So if we go up 2 units from 0, we'll go up to a +2. If we go down 2 units, we'll go down to -2. There is one period. The directions, and they maybe even have set up on the top, I didn't even look, will often say draw 2 periods. Okay? It says draw a complete graph of the function. 1 period is good enough for me. Even if your homework, it says draw 2, just draw 1. You're good. Okay? Let's look at the next example. So what I tried to give you on the next example here, we got 2 slides left. What I tried to give you is a graph that has just about everything you could expect. It's a cosecant, number 1. So it's an inverse trig function, which makes it a little bit harder because we're going to have vertical asymptotes we got to deal with. And I give you everything here. There's this coefficient in front of the cosecant. There's a coefficient of 3 inside the parentheses. We got the -2. Okay? I tried to give you everything that I could, try to make it as complicated as possible so that hopefully you can look at this one example here and get a feel for how to do a lot of the problems in the homework. So instead of giving you 5 or 6 different examples, I'm going to give you one complicated one, and hopefully you can pull everything together from this one example. So here's how we deal with this particular problem. First of all, anytime that there is a coefficient in front of x inside the parentheses, I will always, as the first step, pull it out front. I'll pull it out front of the parentheses, make that a 3 out here. It's going to be an x plus pi over 3. If you distribute the 3, you'd get right back to 3x plus pi. So when I pull that 3 out front, I have to divide both terms by the 3. So that's the very first thing I'm going to do is write it like that. And then I'm going to identify the amplitude. However, I think it's important to know there really isn't an amplitude for cosecant and secant functions. But I'm going to write it down just so that you know it does come into play when we go to graph this. It's 3, but I'm going to kind of circle. It's really not the amplitude. I won't even ask for it on test because I don't want to mess you up with that. I'm not going to try to put it on there to trick you. But remember, amplitude is defined to be the distance away from the center line, and ultimately secant and cosecant functions go up forever and down forever. So there is no maximum distance away. But it does help us identify the minimum values and maximum values for the function itself, okay, when it comes down and it turns around. So we do want to keep track of that number. The rest of this, though, is really important. We do have a phase shift. The phase shift is always the opposite of whatever we're doing to x inside the parentheses. We never have a phase shift unless we have parentheses. And we have to remember it's the opposite of whatever's being done to x. In this case, we're adding pi over 3, so our phase shift is negative pi over 3. Our phase shift is the starting point. That's where we're going to start our graph, and we're going to add our increment from the phase shift. In the method that I use, that's what it'll always represent, is the starting point. We do have a center line, which again is a vertical shift, up or down. The center line is always the number that's on an island by itself. In this case, it's this -2 right here. It's a constant term. It has to be a constant that's added or subtracted to the end of the function. Sometimes they'll put it at the beginning. It'll say -2 plus 3 cosecant, blah, 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 okay? But the key is it has to be a constant, a term by itself. And we always have to say y equals that number. If you don't say y equals, it will always be marked wrong on a test. It is a line, so we want to list it as y equals -2. The last part then, which I think is the hardest, which gives the most problem, I think, when you're going to graph these, is the whole period shift. And in this case, the period, again, in order to find the period, it is always going to be for sine, cosine, in the reciprocals, the cosecant and the secant, is always going to be 2 pi over the coefficient of the x. In this case, is that 3. And sometimes I factored out front here, but it still doesn't matter. It's that coefficient. In this case, it's going to be 2 pi over 3 will be my period. One way to remember the period, if the coefficient is fractional, your period actually becomes larger than 2 pi. If the coefficient is a whole number, like 3 or 2 or 4, your period is going to be smaller, okay? Which means that it's actually going to be a horizontal shrink. It's going to compress the graph. Where if it's fractional, it'll actually lengthen the graph out. It'll make the period longer. Okay? The last thing that we need to identify then to use the method that I use is what I call the increment. And for sine and cosine functions, it's always 1/4 of the period. In this case, it is 1/4 times 2 pi over 3. And when we reduce, we get pi over 6. So what does this pi over 6 represent again? It is simply going to be the angle that we add to get from one angle to the next when we're trying to identify our critical points. For me, you need to identify all the critical points on the graph, which means you're always going to identify where it crosses the center line and the maximum and minimum points if it's a sine or cosine function. Likewise, you're always going to identify where the vertical asymptotes occur or the maximum or minimum points for a secant or cosecant curve. So in this case, it's easy. If we can identify these five values right here, this should be easy for us to graph. We're always going to start by just drawing a nice horizontal line, and that's going to represent our center line. The nice part about the way that I do it, I let you do the labels right on the center line, which is fine. Many times when you look this up in the book, it'll have it drawn the same way. They'll just relabel it. Okay? So we're not going to worry about the up and down part until we take care of labeling these angles. It's always finding the angles that's the hardest part for the students. So let's start. We're always going to start at our phase shift. In this case, the phase shift is negative pi over 3. That's the first point we're going to label. If you get a positive phase shift, you must go backwards until you at least hit 0 or a positive number, so we know where the y-axis should be drawn. If you have a negative phase shift, it's actually easier because then you can just move to the right every single time. Just add your increment. The hardest part is there are still students who struggle adding fractions. We have to get beyond our fraction phobia. We have to be able to do this and do it in our head. We can't jump to our calculator every time we want to add a fraction. So in this case, negative pi over 3 is the same thing as negative 2 pi over 6. The reason why I think of it as negative 2 pi over 6 is because I'm adding a pi over 6. I have to have common denominators before I can add fractions. So negative 2 pi over 6 plus pi over 6 will be a negative pi over 6. That's going to be the next angle that I label on my center line. If I add another pi over 6, I get 0. If I add another pi over 6, I get pi over 6. If I add another pi over 6, pi over 6 plus pi over 6 is 2 pi over 6 or pi over 3. I always expect angles to be in reduced form. And they have to be definitely in radian form. You're always going to have radians along here. It's not going to be in terms of degrees. So don't convert to degrees. It must be a nice radian form and reduced appropriately. And you must identify all of the points. Don't skip points and then just sketch a graph with some of these angles missing. If you're missing the angles, this is really where the majority of the points are. I want to know, can you identify those angles, where those critical points are going to occur? Because we should be able to do it quickly in our head. Negative pi over 3. Again, we have to think about, is this a sine, a cosine, a reciprocal? We need to know that the cosecant is the reciprocal of the sine function. So we start off by treating this just like it is a sine function. So I look at this and I say, oh, this is a sine function. If it's a sine function, it starts on the center line at the phase shift, not at 0, at the phase shift. The phase shift is our starting point. If this coefficient out front was negative, if it said negative 3 out here, if that would have said negative 3, I would have to go down first to start my graph. But since it's positive, I go up first. Then I have to cross before I can go low, cross. I could keep going. I could go high, cross, low, cross. Okay? I even go so far as to dot in the sine function itself. I dot it in as a reference. Do not make it solid. If you make it solid, it makes it look as if it is part of the actual graph, and it is not. It is a reference. If this problem said SIN instead of SCS right here, the dotted picture would be the actual picture. That's the only difference. That's how closely related they are. But if it is a cosecant, if it's the reciprocal, you must, wherever it crosses the center line, dot in a vertical asymptote, because the reciprocal of 0 is undefined. And then again, the reciprocal here, essentially the reciprocal of 1 is 1, so it's going to simply start here, and high points are going to go up, low points are going to go down, because the reciprocal of a really small number is a really large number. Okay? So the reciprocal of a small positive number will become a large positive number. The reciprocal of a small negative number will become a large negative number. There's the picture. Don't forget, though, the last thing that we need to do, and it helps when I can color code this so that you can see it. I know when you're using one color, it may be difficult to remember to come back and fill this in, but I always try to do my axes in red so I can remember to come back and fill it in. In this case, we land on 0. You will not land on 0 for every problem in your homework. You still want to estimate then where it is. It's going to be in between the negative angle and the positive angle. Put it in between the negative and the positive if you don't land right on 0. There's one on the test that doesn't land right on 0. You need to be ready for that. But in this case, we can draw it right here. The last thing we're going to do is label the vertical values. In this case, the center line is y equals -2. The amplitude coefficient, it's really not an amplitude. If I want to be more precise, I would say amplitude coefficient here, because it's not an amplitude. Please understand that, and I won't ask for it on the test. But the amplitude coefficient is 3, which means it's going to go up from -2 up 3 units to 1, down 3 units to -5. There it is. And we can just label it that way. Please understand, the actual y-axis is somewhere between this -2 and this +1. It's probably right in here. If you graph this picture on your graphing calculator, this shape here, the upper shape, is going to certainly be closer to the x-axis than the bottom piece down here, if you tried to graph it in your graphing calculator. And we'll look at it in the calculator tomorrow. I don't want to put it in here and confuse you, but we'll look at it tomorrow. This gives you an idea how this works, essentially, to try to summarize a lot of this. Hopefully everyone can graph just the standard sine and cosine curves using the unit circle. From that, we can expand. If we can identify the amplitude, the phase shift, the center line, the period, and the increment. And all you really need to be able to do then is locate the phase shift, add the increment 4 times in order to get the other critical points that we want to make sure that we graph for sine or cosine. Okay? And then you just have to know, how does the curve start? If it's a sine curve, it must start on the center line. If it has a positive amplitude coefficient, it goes up first. If it has a negative amplitude coefficient, it goes down first. If it's a cosine function, it must start off the center line. If it has a positive amplitude coefficient, it starts above. If it has a negative amplitude coefficient, it starts below. Last piece of summary here is to say, if it's a cosecant, you dot in the function as if it's a sine function. Wherever it crosses the center line, draw a vertical asymptote. High points go up, low points go down. If it's a secant function, you dot it in as if it's a cosine function. Wherever the cosine function would have crossed the center line, dot in vertical asymptotes. High points go up, low points go down. Done. I just summarized that in about the last 2 minutes of talking here. And if you can do that, you can understand that last 2 minutes of what I just verbalized, you should be able to graph any of the sine, cosine, secant, cosecant functions. It's not as difficult as it seems if you just break it down into that little quick synopsis. Now, the tangent and cotangent, a little bit more involved, and we will look at a couple of those later on, but I don't put any of those on the test. You're more likely to see a sine, cosine situation than anything on the AP test. All right, last bit here. Solve these equations. Understand, these are now different than the first ones that we looked at because they're not using the notation tangent to the negative first power of 2.5. In this particular case, they are giving you a domain of acceptable answers. They're saying we want every answer between 0 and 2 pi. Now, this is in radians, so we do not have to give our answer in degrees. We only have to give it in radians. If it wanted it in degrees, it would say between 0 degrees and 360 degrees. It doesn't say that. So, when looking at this, if I'm going to draw a picture, the tangent of x equals 5/2 is the best way to look at this. There are 2 quadrants where the tangent is positive. If you haven't heard of this saying before, please listen to this. Try to remember the quadrants using this little catchphrase. All students take calculus. All students take calculus. And what it means is everything is positive in the first quadrant. Only the sine and its reciprocal, the cosecant, are positive in the second quadrant. Only the tangent and its reciprocal, the cotangent, are positive in the third quadrant. And only the cosine and its reciprocal, the secant, are positive in the fourth quadrant. So if I'm looking for a tangent of an angle that has a positive value, I know that it has to be in the first or the third quadrant. All students take calculus. The tangent is positive in the first in the third quadrant. I still like to draw pictures just to make sure that my angles make sense. Tangent is opposite over adjacent. Opposite, -5 over adjacent is -2. Find the hypotenuse is the square root of 29. Hopefully everybody can do that quickly in their head. Not that we even have to write it down. It really doesn't have much to do with this problem, but it's good if you can identify it quickly. In case later on they ask you to find the cosine of this angle, you could just crank it out now, 2 over the square root of 29. On a problem like this, you must use your calculator. There's no way to get around it. So we'll go to the calculator and we'll do the inverse tan of 5/2. Okay, so I'm going to clear this out. I'm going to clear this here so you can see it. I'm going to go inverse tan of 5/2. And when I do that, I get 68.198. Remember, I'm still in degree mode here. So I want to go mode, go back to radians, because I only need to give my answer in radians. Second quit, and just hit enter again. 1.190. So that's my first answer, 1.190. It's a first quadrant answer. So x, 1.190. You have to also understand how the angles work in terms of radians. Don't just memorize everything in terms of pi. So yes, this angle here is pi over 2 or 90 degrees, but you also need to know that pi over 2 is a decimal value. Okay? It's half of pi. If pi is 3.14, then pi over 2 is 1.57. So the first quadrant has to be some decimal value between 0 and 1.57. 1.19 is between 0 and 1.57. It's a good answer. We also need to find the third quadrant answer. So in addition to having this angle, now I need to have this angle because it gave me a domain of acceptable answers. In this case, it's straight across from the angle. So the easiest way to find the next angle is to just add pi to that value. So if I come back to my smart calculator and I just add pi to it, I will get a value of 4.332. Come back and I'll list my second answer as 4.332. You should ask yourself, does that make sense? Do these two angles make sense? And the answer is yes. My first answer is between 0 and 1.57. My second answer is between 3.14 and 4.71, whatever 3 pi over 2 is. Okay? It's acceptable. For the fourth quadrant, should be between 4.71 and 6.28, because 2 pi is the same as 6.28. So not only do you have to be able to think in terms of degrees and radians in terms of their pi value, but you also have to understand what those values actually represent. That pi over 2 is 1.57. That 3 pi over 2 is about 4.71. You need to be able to recognize those values. Now, some we won't need our calculator for, and I don't want you to use your calculator if you don't have to. The cosecant of x equals 2. I would much rather see you write this as the sine of x equals 1/2. If we can rewrite using sine, cosine, tangent as opposed to the reciprocal identities, do it. We recognize it more, we use it more, everything should be good. In this case, again, we want a complete rotation. In this case, they don't have an equal to, which is fine. I don't know why they left it out. It's an open interval. Either way, it doesn't really matter because 0 or 2 pi are not answers here anyways. So it really doesn't make much difference whether they had an equal to there or not. However, we need to know all students take calculus. The sine function is positive in the first and second quadrants. And in this case, we want both answers because they list it this way. If this would have said CSC to the negative first power of 2, then we would only list one answer. It's all about how they ask it. It's just a notational situation. You have to know how are they asking the problem. So sine, opposite over hypotenuse, opposite over hypotenuse. makes this the square root of 3, negative square root of 3. How do I know that? You can use your Pythagorean identity if you want. 2 squared root is 4 minus 1. Take the square root, but you should have it memorized. It's a 30, 60, 90 special right triangle. Across from 1 is the 30-degree angle in this 30, 60, 90 special triangle. Across from the square root of 3 is a 60 degrees. So in this case, my answer would be 30 degrees and 150 degrees because it's 180 minus 30. However, it only wants the answers in radians. Don't even circle those answers. Those are not acceptable. You need to know that 30 degrees is the same as pi over 6. Here's what I was talking about earlier when I was talking about the rotation of angles. Too many times students want to convert this and say, oh, this is 150. I got to multiply by pi over 180 and then reduce it down, and it takes forever. You should be able to rotate this in your head by simply saying, if 30 degrees is pi over 6 and you have that memorized, you got to know that. 150 degrees is simply 5 30-degree angles. That's what it is. It's 5 30-degree angles. That's why it's 5 pi over 6s. If it's in radians, it's 5 pi over 6. Done. You should be able to find multiples of pi over 6, pi over 4, pi over 3, pi over 2 without having to convert. Just think about what the multiples are in your head and convert those in your head. I'll do the same thing here when I'm doing the arc sine of a negative number. This time it's the arc sine of negative 1/2. If it would have simply said sine to the negative first power of negative 1/2, you would only give one answer. But in this case, they're saying give me every possible answer. Well, how do we do that? I mean, this goes on forever and ever and ever. It's periodic. It doesn't end. There's infinitely many solutions. I'll talk to you about how we can summarize this down then when we list our answer. First thing we need to do, all students take calculus. The sine function is positive in the first and the second quadrant. Therefore, it is negative in the third and the fourth quadrants. So we draw ourselves a picture. I will draw the triangles every time. Many of you will get tired of it. You'll be, I already know how to do this. Why do I have to show the work? The more you do it, the better you'll get, and the less likely you will be to make mistakes. If you label it in the correct quadrant, you won't make the sign mistakes that a lot of students make. In other words, it's opposite over hypotenuse. I'm going to label this negative 1, this 2, which makes this the square root of 3, and it's actually negative. Now, why am I always labeling that third side when it really doesn't matter? Because if they come back and then they ask later on in the question, what's the cosine of this angle? I know it's a negative square root of 3 over 2. Or what's the tangent? I have everything labeled, so I can find any trig value now that I want. Over here, opposite over hypotenuse makes this the square root of 3. Again, I wish I had picked a different value here because we get another 30-degree reference angle. I wish I would have picked something a little different, but it is what it is. Okay. The key part to this is how you list your answers. If you think about it in degrees, I don't mind you thinking in terms of degrees at all, but then you got to convert it to radians. So here's 180 plus 30 is 210 degrees. If I come around here, this is going to be 330 degrees. Okay? Now, the best way to really write those, though, is to not consider this to be 330 degrees, but instead to call it probably negative pi over 6 would be better, okay? Or negative 30 degrees if we're thinking in terms of degrees. Just go the negative distance. Okay? Then we got to convert these to radians, though. 210 degrees. 210 degrees is 7 30-degree angles. It's 7 pi over 6. Negative 30 degrees is negative pi over 6. And if you wanted to call it 330 degrees and call it 11 pi over 6, it would be fine in this particular case. It would be fine. Because that's really how we would list it if it said to go between 0 and 2 pi. So if you listed it as 11 pi over 6 on a problem like this, that's fine. But how do we represent then that there's infinitely many solutions to this? And here's the key. Yes, it's 7 pi over 6, but any rotation of 7 pi over 6 will also work. So if I go around again and add another 2 pi to this, that angle will also work. If I add 4 pi, it will work. So how we represent any rotation of this angle will also work is by adding a 2 pi n to the answer. Add 2 pi n, where n is assumed to be an integer, any integer value. If n is 0, then it's just 7 pi over 6. If n is positive 1, it's a positive rotation. If n is negative 1, it's a negative rotation from this. Okay? And you don't have to write where n is any integer. I'll let you just write 2 pi n. Assume that you know it's when n is any integer. Well, this lesson is a lot longer than I thought it was going to be. It's an hour long. If you happen to get some of the notes, great. Here's the assignment. If you do want to work on it tonight, it's good to get a good start on this, and we will talk about this in class tomorrow and hopefully get to some questions as well. Don't forget, we are going to take a short quiz on section 1.2, just 1.2. We'll do a quiz on 1.3 on Tuesday. Okay, hope everybody has a great night and look forward to seeing everybody in class tomorrow.